Okay, hi everyone, and welcome to the January 2015 MAPP webinar. Thanks for joining today. We have a webinar today on the topic of Arctic modeling, and we're going to hear one talk on model development, specifically on the glacial calving process, and two talks that are more in the area of prediction. So one talk from our colleague Hal Ritchie at Environment Canada, and he's going to talk a little bit about some specific marine Arctic predictions that they're working on in particular areas of their prediction domain for EC. And then we're also going to hear from Wanchu Wang from the Climate Prediction Center here at NOAA CPO, and he's going to talk a little bit about initial conditions for CICE prediction, for seasonal CICE prediction in the climate forecast system. So as I mentioned, we have three talks, and our format is to do each of the talks with about 15 minutes for each talk, and then hopefully if we stay on time, we'll have about 5 minutes for questions for each of the speakers, and we do questions immediately following each of the talks. And the way that we'll do questions for those attending remotely is I'll ask you to raise your hand. So the way to do that is to navigate to the participant list in WebEx, and at the bottom of the participant list, you'll see a little logo with basically a hand symbol, and if you click that, it'll show me that you have a question. I can unmute your line, and you can have a discussion with the PI. You can ask your question and any follow-ups that you might have. So I'll give a reminder about that, and one thing that I would advise is when you see that we start getting towards the end of the slides, you know, the summary slide comes up, maybe start finding that button so you can, you know, raise your hand right about when we open the question session up. So thanks again to everyone for joining, and thanks to the three speakers that we have. I'm very excited for these presentations, and we're going to start first with Olga at GFDL. So Olga, are you on the line?
Yes, I am.
Okay, great. So I'm going to transfer control over to your computer.
Okay.
And then just share your screen.
Okay.
Great. Yeah, whenever you're ready, go ahead.
All right. So I will be talking about calving, and specifically about calving from outlet glaciers, and I'll cover observational part and what we are doing with respect to that in terms of modeling. Just a reminder that calving and icebergs, they come in all different shapes and sizes, and this slide illustrates that. The picture on the bottom left, it's an aerial photo taken from near the front of the Ross ice shelf. It's an iceberg that's still attached to it. It's called nascent, so it hasn't calved yet. Usually such big tabular icebergs, they calve twice per century. They're quite big, about 100 kilometers long, about several 20 to 30 to 50 kilometers wide, and as I said, they calve roughly twice per century. The picture on the bottom left, it's a satellite image after Larsen B ice shelf collapsed in 2002, in March 2002. Such events are fairly rare. It was stable since at least last glacial maximum, but it's also one kind of an event of calving event of like on end spectrum of calving and icebergs in that regard. And pictures in the right column, it's an aerial photo of Jakobshavn iceberg in Greenland, and the other one on the bottom right is Columbia Glacier in Alaska. Calving from those glaciers happen much more often. From Jakobshavn iceberg, it's more like seasonal calving. From Columbia Glacier, it happens pretty much all the time. Those little bits and pieces fall off mostly on hourly basis. And today I'll be focusing specifically on outlet glaciers and tidewater glaciers calving. It's these two representatives here. In the past year, a PI on this project, Liz Stearns, who is in Kansas University, she has been compiling data from Halheim Glacier. It's located in the southeast of Greenland. It's this red dot over here. What you see on the left image, it's a modest image of Halheim Glacier, and these dots, it's locations where the glacier flow speed was observed continuously. So these dots are 5 kilometers apart. And a summary of these observations is presented on the plot in the middle. So the time goes from 2001 to 2013-14. It's on vertical axis. On horizontal axis, it's the location of these points, or where the observations of ice speeds were taken, and it's from very top left point towards the ice front. And as you can see, so the color shows the ice flow speed. As you can see, the whole glacier sped up around 2003-2004. And an interesting thing that this speed up propagates from the ice front towards interior of the glacier. Interestingly enough, it also coincides, or sometimes not coincides, with calving events, and those could be deducted from terminus area, which is shown on the very right plot. For instance, there was really big calving event around 2005, summer 2005, and you can see like very bright colors in ice flow, and that signal propagates upstream. So in order to understand and have an idea how to model all these events, I'll back up a little bit. So another piece of information that Listerns collected is the melange. It's a collective term for little bits and pieces that fill the fjord in front of the glacier. Halheim is in the very left bottom corner of this image, and depending on the presence of this melange, the ice front of Halheim advances and retreats and affects the flow of the glacier upstream. So what has been done is all those satellite images, they were digitized to produce more kind of palatable information what can be deducted about icebergs or sea ice, and this is summarized on the bottom plot. So the terminus area is shown in red, and melange area is shown in pinkish. Those blue bars show where the melange was completely solid. So all this information, what I showed on previous slide, in here is used to get an idea how tidewater outlet glacier behaves and when it's calving. This is summary showed from work by Jason Amundsen, who is a PI, again, on this project. He's in Alaska, and the idea is the following. When the glacier is advancing and those two different U's, U sub T is a terminus velocity, and U sub B is the balance velocity. When those velocities are close to each other, the sensitivity of the whole glacier to small perturbations, either in accumulation rates or in melting in front of the glacier, are substantial for the behavior of the whole glacier. When the glacier starts retreating, and again, those two velocities are pretty close to each other, the sensitivity to changes decreases. But as soon as calving starts to occur, the glacier doesn't care anymore about what's happening outside it, and it just continues to retreat until it finds a new stable position, and then it starts to slowly advance again and start feeling what's happening around it and what accumulation rate it is doing, or what, for instance, the temperature in the fjord might, how it might affect it. And this is summarized on two bottom plots. What it shows is the calving rate from this glacier depending on the elevation of the grounding line. And as soon as the glacier advances into deeper waters, it starts to calve with a higher rate. But when it starts to retreat backwards, there is no relationship between calving rate and the depth of the water, meaning that there is no sensitivity to the environment with respect to calving rates. Another aspect that we were working, and myself and Doug McHale at the University of Chicago, is the understanding of what's happening when the new ice front just formed and how all those structures start to appear. What you see on the left image is an aerial photo taken at Larsen B right after it collapsed, and those fractures are clearly seen very close to the ice front, which formed like within days or weeks prior to this picture. And we have been developing a new treatment for the effect of bending of ice front due to the imbalance in hydrostatic pressures on both sides. So what the image on the right shows is the elevation of 200-meter thick ice shelf for a glacier. As you can see, the surface kind of bends down, and in response, there are stresses that are produced due to such deformation, and at some point those stresses exceed critical stress or yield stress, and those fractures occur. And the reason why we are working on all of this is that outlet glaciers and tidewater glaciers are quite small, and it's pretty much impossible that each of them will be individually resolved in global scale or global ocean model. What I'm showing here is simulation that has been done here with a new MOM6 model. It's 1/8 of a degree. The point of this work is that we can resolve big ice shelves and ice shelves in Antarctica. So you can see the mixed layer speed in these areas in the cavity, so the circulation is resolved in the cavity. However, around Greenland, all those little fjords and outlet glaciers won't be resolved, so we need to parameterize those processes that are happening around Greenland. In Antarctica, what you are looking at is a movie showing the ocean surface speed and the sea ice extent in these simulations. So in Antarctica, there is a hope, and it's our actually next step is to put large tabular icebergs and simulate calving events from big ice shelves. So with that regard, those big tabular icebergs will be resolved explicitly. However, for Greenland and other locations where calving can occur, we need to parameterize those processes. So to summarize, so far, we have identified and compiled a set of observations that we need to collect and observe on tidewater and outlet glaciers. There is a new parameterization that can explain calving from those glaciers. We also have developed a new treatment of ice shelves from fracturing, and we are busy putting all that into global ice ocean model. The next step would be to try to resolve large tabular icebergs and the interaction with the ocean. So I'll stop here.
Great. Thanks a lot, Olga, for the summary of your progress on your project. So we have time for questions. We have a number of minutes for questions if anyone has one. So for those who are logged in virtually, the way to do this is to go to the participants list and use the raise hand feature. And once you put your hand up, we'll see that you have a question, and I can unmute your line and you can ask. In the meantime, does anybody in the room here have a question for Olga? So I'll just wait a few seconds, Olga, with some awkward silence here and see if anybody raises their hand. Yeah. Sometimes it takes a minute to find that button. If you're having trouble finding the button, you can also send me a chat message to let me know that you have a question. But I don't see anything coming up yet, Olga, so what we'll do is move on, and if anyone ends up having a question later, we can maybe come back to it. So, okay. Olga, thanks a lot. Okay, the next speaker is Hal Ritchie. Hal, are you on the line?
Yes, I am.
Great. I'm going to transfer control over to your computer.
Okay.
And share your screen and bring your slides up and take it away.
Oh, okay, quick start. Share my screen. Okay, and start the presentation.
Great, go ahead, Hal. Thanks.
Okay, well, thanks to you all for joining in, and it's a pleasure to get this opportunity. This presentation will be a fairly quick overview of an integrated marine Arctic prediction system for METAREAs, and co-authors are essentially leads of the different science support technology transfer activities in this initiative. So Pierre Pellerin is our component lead. I'm acting as senior scientist. Luc Filion is leading the atmospheric data assimilation. Greg Smith leading the ocean ice and sea ice uncoupling model. Mark Buhner for sea ice data assimilation. Tom Carriere for iceberg ice hazard modeling. Diane Johnson for satellite products, atmospheric ones. And Natasha Bernier is leading the wave model research and development. And Serge Desjardins for the wave model products and services. So a bit of background. As we're all aware, decreasing Arctic ice cover has resulted in an increase in navigable Arctic waterways. So in anticipation of increased marine traffic, the International Maritime Organization established 5 new areas covering the Arctic. And in 2007, Environment Canada and the Department of Fisheries and Oceans expressed our willingness to become an issuing service for METAREAs XVII and XVIII that I'll show on the next slide. And then in July 2010, Environment Canada started issuing meteorological maritime safety information for those areas on a test basis. So here you see the new METAREAs with areas 17 and 18 being the pie-shaped areas covering essentially northern Canada up to the North Pole, but also extending over Alaska to some extent and also into Greenland. I should say these are areas for issuing and not necessarily for producing the forecast. Our main activity is to develop an integrated marine Arctic prediction system in support of those monitoring and warnings, and specifically to develop a short-term marine forecast system using a high-resolution regional coupled multi-component, that's atmosphere, land, snow, ice, ocean, and wave, modeling and data assimilation system to predict near-surface atmospheric conditions, sea ice concentration, pressure, drift, ice edge, freezing spray, waves, and ocean conditions, especially the temperature and current. But also there's an improved Arctic monitoring component with this. And the sketch here in the top right, the blue triangles here represent new on ice or in water drifting buoys, so they drifting around. This isn't a real configuration. But also the red stars indicate new coastal stations that are being set up under this METAREAs activity. And some of those ice beacons are largely being deployed with the help of the Department of National Defense, illustrated here with some ice beacons being sent down by parachute. And the deployments scheduled for 2013 are shown in this figure here on the right, with more of them having been deployed earlier and later this past summer as well, as part of the activity. This is also part of our Canadian Operational Network of Coupled Environmental Prediction Systems, which is an interdepartmental collaboration among Environment Canada, Fisheries and Oceans, and National Defense to develop coupled prediction systems, atmosphere, ice, ocean forecasting systems, by coupling the Environment Canada Global Environmental Multi-Scale, or GEM, atmospheric model to the NEMO, or Nucleus for European Modeling of the Ocean, which is the ocean model supported by Mercator-Océan, with whom we're collaborating. They are an operational oceanographic group, and actually Gilles Garrick from there is a co-author on this presentation. So here we see some of the concept systems that are existing or under development. Quarter-degree resolution global system for medium-range forecasting, a 1-degree system for monthly to seasonal forecasting, this variable resolution North Atlantic on a 1/12 of a degree grid, and I'll say quite a bit more about that in this presentation, for short to medium-range forecasting. There's also a high-resolution 136 Grand Banks model for the Northwest Atlantic, largely for emergency response. The Gulf of St. Lawrence system illustrated here that I'll say more about in the coming slides. And then the Gulf of St. Lawrence system that's being set up for short-term forecasting on a high-resolution grid. So here we're building on the Gulf of St. Lawrence system that, in fact, has been operational since June 2011, initially doing 48-hour forecasts once daily at 0 Greenwich Mean Time, based on coupling the GEM model and 10-kilometer grid, version 1 of the CICE ice model, and the Societal Gulf of St. Lawrence ocean model on 5-kilometer grids. And then just this past November 18th, an updated version of GEM and was implemented with the NEMO model and version 4 of CICE now used in the system. Just to illustrate that the coupling does make a difference, here we have a test case for March of 2012 with the coupled minus uncoupled differences shown for sea ice and temperature on the left and right panels on the top. So here we see in terms of sea ice differences in ice concentration of quite a few tenths of concentration. I should say in the uncoupled system the initial conditions are persistent, so the ice concentration, for example, would not change. And then the impact of that on the 2-meter temperature shown in the right panel, differences of the order of 7 or 8 degrees over the opened up water during this case of rapid ice change, and along the coast several degree differences at the stations where we verified. Also in the summer there are important differences with upwelling cases, shown here for July case with the differences for 10-meter winds on the left, and again a couple of degree temperatures, Celsius differences on the right. And also there is, I mentioned under development with a 1-kilometer version of the NEMO model and a 2.5-kilometer version of the GEM model for the Great Lakes, and this is in particular for support of the upcoming Pan Am Games this coming summer. Last year's ice season was very active, so here we show evaluation against all surface temperature observations, 48-hour forecast for January to March of 2014. Colors here show the biases, and standard deviations are reflected by the size of the circles here. I realize you don't have time to see them in detail, but when we evaluate the coupled versus uncoupled results, we find smaller errors over the coupled system over water, and then this illustrates that the Gulf of St. Lawrence is actually an ideal laboratory for studying the impacts of coupling. For the atmospheric model and data assimilation aspects, we recently had, again on November 18th, 2014, a major implementation, and METAREAs is benefiting from improvements from the regional deterministic prediction system and the global system, especially for surface boundary layer fields. So on that date at the Canadian Meteorological Center, the global ensemble system was upgraded. A 4D ensemble variational data assimilation method went into both the global and the regional systems, and also there's an upgrade to the regional ensemble prediction system. I mentioned the regional coupled system for the Gulf of St. Lawrence was replaced on that date, as well as a 2.5-kilometer pan-Canadian domain version of the GEM model going in experimental mode. I'll just say that improvements up to 2 days in the regional system, which is the limit of their forecast range, and up to 5 days in the global system out of the 10-day predictions for the global system were observed, and that justified the implementation. Led by Greg Smith with a team in Dorval, we also have the Concepts Global Ice Ocean Prediction System that on the quarter-degree grid, and I should mention that the NEMO grid is actually variable resolution, so it gets as fine as 15 kilometers over the Arctic with the CICE model on the same grid. Using the Mercator-Océan data assimilation system incorporating sea surface temperature, and salinity profiles, and anomalies from satellites in the assimilation. And also there's a 3D VAR ice analysis system in ingesting satellite data, Canadian Ice Service charts, and radar sat image analyses. That was implemented experimentally last March to provide boundary conditions for regional systems, initialize seasonal forecasts, provide emergency response guidance used for coupling with the global GEM model in the both the medium range and seasonal forecasting, as well for ice forecast. And then there are various products displays available for those. The regional ice prediction system was upgraded recently as well. So it runs on this Arctic grid on the 1/12 of a degree variable resolution, which goes from about 8 kilometers in the south here up to as fine as 2 to 3 kilometers in the Arctic archipelago. The previous system, version 2.0, was on a 5-kilometer grid covering North America on sort of a lat long or a Cartesian grid, actually. And the new grid is now on this regional 12th of a degree grid. The new system is initialized from the global ice ocean prediction system fields for the mixed layer depth, sea surface temperature curves, and thicknesses, where the previous version used climatology. And this is a bit more detail on the systems. 4 analyses and forecasts per day. The analysis system led by Mark Buhner and others in publication at the moment, and I mentioned that the fields that it ingests. It operates on a 6-hour cycle and just uses the previous analysis at this stage as the first guess for that cycle. And then the forecast system, again, is based on the CICE model, forecasts up to 48 hours, and that's being documented in an article now. Here we see an example showing the RITS 2.1 initial conditions versus the Canadian ice surface daily chart, so good comparison there. And then the 42-hour forecast in this case for one case. Again, generally good intercomparison. And again, there are various visualization packages for those sea ice analyses and forecasts. So again, our objective is to produce this coupled meta-area integrated system. What we're moving towards now is, again, GEM on a 10-kilometer grid driving the system with NEMO CICE on the grids that we just looked at. WAVEWATCHIII is the wave model, and we're also moving towards 3 to 5 day ensembles. There's iceberg ice hazard models, an automated system revised and implemented recently. Target detection software packages acquired and being evaluated. Ground truth data being collected from ship and iceberg observations. And development work on the ice island and ensemble iceberg forecast models, as well as probabilistic iceberg products. Wave modeling earlier on in this activity, a WAM-based grid for the Arctic was implemented. In this grid here, the ice mask is stationary, as I mentioned, but will soon become interactive with the model outputs, especially significant wave height, feeding both the regional and global marine product matrices. But just say we now have research and development in progress with wave ice interactions under 2 projects shown here. And in this wave ice forecasting interaction framework that's being developed, we're changing from WAM to WAVEWATCHIII, which is being coupled with the CICE4 to look at the impact of waves on ice flow distributions and vice versa. And in particular, we want to improve the predictions of waves, ice, as well as the location of the marginal ice zone. And radar-sat imagery is being used here to help and evaluate these systems. The final products are the atmospheric satellite products produced by the Ontario Lab for Nowcasting and Remote Sensing, developing single-channel enhancements using MODIS data to improve weather monitoring, multispectral imagery using MODIS for products such as fog and stratus, snow, ice clouds, water cloud depiction, and again, depicting fog and icing, and advanced process to use in the NEMO workstation that's used operationally in our weather forecast centers in Canada, for example, to determine cloud, no cloud, stratified cloud versus convective clouds, cloud top height, and characteristics for severe weather signatures. Here's an illustration of some products for a demonstration case running from June into July 2013, showing the distinction between ice and clouds using some of those products. And these are being documented, training being provided to the Canadian forecast centers. And then a couple of more illustrations showing the advantage of going from the true color depictions to the multispectral where the distinction between clouds, open water, and sea ice is much clearer in the multispectral products. And similarly, comparing with infrared and multispectral products for sea ice streamers, sea ice, and open water depictions. So in summary, building on the operational coupled atmosphere-ocean ice forecast system for the Gulf of St. Lawrence, an integrated marine Arctic prediction system is being developed in support of the meta-area monitoring and warnings. Wave model, sea ice model, and sea ice data assimilation component systems have been developed and are being implemented operationally. Good progress is being made on improvements to all components, combining them for the implementation of the fully coupled system. This is a flagship, what we call a signature project for the Meteorological Service of Canada. We're now approaching the end of Phase 1 and have prepared and submitted a proposal for Phase 2, which is under consideration. So that's a rather quick tour through what I wanted to present. Thank you.
Great, Hal, that was great. Thanks for telling us about what you're up to at EC. Again, we have time for questions, and just as a refresher, the way to ask a question is to use the hand raise feature in WebEx, which you can access through the participant list. You can get to the participant list by going to the bar that should be at the top center of your screen, and if you just put your mouse over that, you'll see the participant list. You click on that, open it, and the raise hand feature should be on the bottom left. And I see a couple people figured out how to use it, so we will take a couple of questions first from Eric Baylor. Eric, are you on the line?
Yeah, I am. My interest is in the sea ice data assimilation question, and that is, when the sea ice data that you assimilated in your model, do you have a man in the loop on that data, or is that completely automated?
Okay. It's completely automated, but I will say that among the fields that are put into the assimilation system, we do have the Canadian Ice Service analyses, which they are largely people-produced, and also the radar sat imagery from the Canadian Ice Service, again, which has a considerable person input to those fields. But they are treated, as automated. The system itself is automated, and given that those inputs are available, then it's an automated system.
Well, the reason I ask the question is because in order to do true assimilation, you can't really have a man in the loop because it changes the uncertainties because you can't exactly replicate from time to time, and that's why I was interested, particularly with respect to the Canadian synthetic aperture radar data, i.e. radar sat.
Yes. Yeah, I take that as that's a valid comment. We're moving, they are moving towards more automated assimilation methods for the radar sat, but it's under development.
Thank you.
You're welcome.
Okay. Thanks for the question, Eric, and make sure to put your hand back down in WebEx. So the next question is from Renee Tatusko. Renee, are you on the line?
Yes, I am. Thank you very much. Hi, Hal. This is Renee Tatuska from the National Weather Service, Alaska Region Headquarters. Very much appreciated your presentation. I do hope it will be shared because I do want to be sure that this is shared very broadly within NWS. I have three specific questions. I know you mentioned the WWW, the WAVEWATCHIII, and that's a collaboration, I'm assuming, with the Ocean Prediction Center. Are you also engaging with either the Climate Prediction Center or the Environmental Modeling Center and or the Navy?
Okay. Yes, well, we're definitely, the WAVEWATCHIII is very, very collaborative with Hendrik Coleman and his group. We have had interactions with some folks in the NWS, predictions such as Bob Grumbine, and you probably recall our participation in the workshop that was held in Boulder last May that you were there as well. In terms of direct collaborations with the data or the climate groups, I'm not aware of any that were directly involved in METAREAs. There may be some of our researchers that are involved in collaborations, but I'm not up to date on those.
Okay. And then when I listened to your presentation on the prediction and the marine forecast systems, I'm sure you're probably aware that the World Meteorological Organization is in the process of establishing a global integrated polar prediction system, GIPS. So given your responsibility for those two MET areas, it begs the question, what is your engagement with the other MET services to ensure a quote-unquote integrated prediction system capability?
Okay. Maybe I'll ask. First of all, we're quite involved with WMO, and especially through the World Weather Research program that is partly sponsored by WMO, and looking very much forward to the year polar prediction involvement. And Greg Smith, who featured quite large in the presentation that I just gave, he's on the committees preparing for the year polar prediction. So, and we're fully involved in interactions also with the G'day Ocean View activities, the intercomparisons going on there. And again, Greg is quite involved in those. Maybe we could ask, I'm not sure if Greg is on the line. He was thinking of participating, and he might be able to join in to add further comments. But so we are connected with international activities through the WMO, and especially through the World Weather Research Program and the upcoming year polar prediction.
Okay, that's great. We can probably take this discussion offline. I was just curious, last question, have you had any discussions, say, with Russia or Finland or Norway or Denmark, with any of the other Arctic countries regarding their efforts to develop, an integrated prediction system, either for the marine or the ice?
Yes. In fact, we just recently had an inquiry from a research scientist at the Norwegian Met Institute, and I have given similar presentations to. There was a working group meeting here a while ago in Halifax involving all these nations. So they're aware of our work, and I think there's growing interest in possible collaboration. Yeah.
Great, good to hear. Thanks very much, Hal.
And just to add that as Dan mentioned at the beginning, this webinar is being recorded, so I'm sure this will all be available.
Fabulous.
The slides and the recording should be available in the next day or so on our website.
Great, thank you.
And Hal, I don't see Greg in the attendee list, so I would have unmuted him, but I don't think he's logged in at the moment. I might be missing him, but anyhow.
Okay, well, thanks for checking.
Yeah, absolutely. So there are no more questions. And Renee, also, if you could put your hand back down in the participant panel, that would be great. Oh, actually, there's one more question which we can take quickly. Well, it just came out. Okay. There was a question that came in and out. So if that comes back, maybe we can go back to it at the end of the webinar. But otherwise, Hal, thank you so much for that overview and taking the questions. Really appreciate it.
Okay, you're welcome. Thank you all.
So our next speaker is Wenchu Wang from the Climate Prediction Center at NOAA. And Wenchu, are you on the line?
Yes.
Okay, great. I'm going to transfer control over to your computer.
Hi, good afternoon. This is Wenchu Wang from CPC, Climate Prediction Center. Yes, I've been talking about CFS, CS prediction. CFS was implemented in 2011. It was probably one of the first 2 or 3 operational models that includes a dynamic CS component. And before I continue, I want to acknowledge the support by STI, and also thank Jinglan Zhang from University of Washington for providing parameter CS data. With that, we made some experiments to show the importance of initialization of CS. So there are already a couple of papers analyzing the CS prediction from CFS, and one thing we noticed is that the actual prediction skill here on the left panel is say for September is about 2 months or so, and the potential predictability is much higher, and it's beyond the target, the whole target period of the CFS forecast. That's beyond the 9 months. So one thing we want to analyze is what caused the gap between the current predictability capability and the potential predictability. So generally there are two reasons. One is initialization, and the other is physical parameterization. So in this short talk, I want to start with showing you some forecast CS errors in the operational CFS. Then I will discuss what could cause these errors. Then we'll talk about what we can do to improve it. So the forecast errors in the CFS. First, let's look at the climatology. This is the left panel is forecast for August from March initial condition. So that's like a 5-month lead. The main thing we notice is the model forecast CICE concentration or coverage is wider than the observation. Here, the color in the shading is the concentration from CFS, and the blue lines, blue curves are the observed 15% concentration. So in particular, when the very important area we want model to have a good forecast is the CICE. We see that the model has a wider is to the south of the observed 15% concentration. That means the model melting is too slow. And the red panel is the forecast for November and from June initial condition. So and here we see a opposite arrow. That is, the November is when the sea ice expand towards the south, and here we see the blank. That is in CFS forecast, while the observed is already to the near the Bering Sea. So this is a climatologic arrow, and in addition to this, we also look at the more detailed errors. Here we look at the zonal mean concentration around the Bering Sea and the CICE Sea between 170 degree to 200 degree east. The top left panel is observed concentration. We plotted from June through December as a function of season and latitude. Here's the average for 5 years average from 2009 to 2013, and the upper right panel is from CFS. We see that the observed has a very clear seasonal cycle, and the forecast from CFS is from March initial condition. We see that the model has a very weak seasonal cycle, so it failed to predict the melting as in the observation, and also the freezing is also delayed compared to the observation. So there are basically 2 errors, major errors: slower melting in summer and slower freezing in fall. So that's the errors. So the question we want to address is what caused these errors. So again, there are two categories of the possible reasons. One is in initialization, and the other is in physics. So for the initialization, we look at the CS initial CS extent first, and the top panel here shows the initial CS extent from that is used for CFS, which is CFSR, Climate Forecast System Reanalysis. And we compare that with the NASA team observational estimate. And one main thing is that we see that before 1997, the CFSR is lower, slightly lower than the NASA analysis, and after that is higher. And the bottom panel shows the difference between CFSR and the NASA analysis as a function of the year and the season and month. And again, we see a discontinuity around 1997, and there's another one which is in 2008. So this kind of thing will cause the large errors in the forecast. So making the bias correction very difficult because the errors are not stationary. And another thing is the CS thickness. So for CS thickness, we compare the satellite retrieval in the top panels. We compare eyesight with CFSR, and the red panel is the difference. We see that the CFSR is thicker than the satellite retrieval. And in the lower panels, we compare another product, which is called PILMS from University of Washington. We see that the PILMS and the satellite retrieval are more consistent, more similar. And the difference is similar to the comparison with satellite. So this basically suggests that PILMS is a better product compared to CFSR. And one question is, so what if we use a better initial CS thickness? Are we going to get a better forecast? And in addition to that, we also look at the interannual variability. Here we look at the top panel shows the anomaly CS concentration from PILMS, June, July, August for 2012, and the lower panel is from CFSR. We see that CFSR anomalies are much weaker, and also the model failed to predict the minimum, the minimum September minimum CS extent. So given these differences, it's possible that if we use PILMS CS initial condition, the forecast could be better. So that's the hope. Another thing is the physics, the model physics. There are also some treatment in the model physics that may cause the errors. Here I will just read this, and I'm not going to show you the details. So the main thing is the model has too few clouds, and that caused too much solar radiation, and that in turn caused the warm bias in SST. And also there's another treatment that is used to balance this warm bias. That is a constraint in CS bottom heat flux. So these two together cause some issues in the model. So I skip this. I just give you a quick idea what the issues are in the current operation CFS. So first is initialization problem. We have a jumps in concentration, one in 1997, the other is in 2008. And also we see errors in CS thickness. So, and for physics, there are warm bias in SST, that is due to the solar radiation, and also the bottom heat flux. So, the main thing is what can we do to improve this? So the first thing is we want to improve the initial CS thickness, and before that we just tested the use of the alternative CS thickness. Eventually, we want to develop another initial condition that is consistent with the forecast model. So, but for now, we just made some experiments to test the impact of initial CS, and then we also modify the model physics to see to what extent the modification to the model physics can improve the prediction. So this slide summarizes the results that demonstrate the improvement. Here we have 4 panels comparing zonal mean CS concentration between 170 east to 200 east. And this is a 2009 to 2013 average observation. We see a clear seasonal cycle. And CFS, we see a very weak seasonal cycle, so it's too slow melting and too slow freezing. Now, without changing the model, we just simply replace the initial condition. That is the lower left panel here. That improved the seasonal cycle compared to the standard operational CFS. So that means using a better initial condition does help improve the prediction. And however, we see that the melting doesn't go as far as in the observation, and also the freezing is also a little delayed compared to the observation. So with the additional modification to the model physics, that is, we use the we increase the cloudiness that allows the less styles in SST, and we remove the bottom heat flux that further improve the prediction in the seasonal cycle. So that means in addition to the initialization, the model physics is also very important in the current system. And that's basically it. So in summary, we need more consistent initial concentration and a more accurate initial CS thickness. And the current model also needs some modification to reduce the model bias for better forecast. And let me check. Okay, that's what I have. Thanks.
Okay, thanks a lot, Wanshu. That was pretty compelling results. So we have a bit of time for questions for Wanshu. If there are any questions, again, in virtual land, just use the raise your hand feature in the participant list, and we can unmute your line. Any questions in the room? Yeah.
I have a question.
Yeah.
Do you have a sense, I don't know if you had a chance to look at this yet, but do you have a sense of whether your improved CICE predictions affect the seasonal prediction for other variables in the Arctic or even beyond that?
No, we don't look at other variables, but the hope is better CS prediction will also lead to better prediction for other variables. But we didn't look at more other variables yet.
Thanks, Heather. We have 3 questions online. The first is from Sean Helfrich. Sean, are you there?
I'm here.
Okay, great. Go ahead.
The first, I guess, is a comment. I had 2 things, I guess. One is a comment about the utility of, I know you've compared the CICE thickness to a couple of other products, some satellite-based products. The use of NSIDC data as your comparison along the ice edge, it probably is even more drastic if you actually compared that to a SAR-based ice edge or a visible image-based ice edge. The ice edge that NSIDC uses is from passive microwave, so it probably is off, we've noticed it off very typical in the summertime of hundreds of kilometers. And from a navigational standpoint, that's kind of an unacceptable line if you were to try and even apply their product towards navigation. So I think it needs some comparisons to ice edges that are used for navigation, such as the one the National Ice Center winds up creating. And there has been some work done over at NRL doing comparisons of the ice edge for their Arctic Cap Nowcast forecast system.
Yes. Yeah,
the other thing that I just wanted to see is that I'm glad you pointed out, and I can't say that the results were all that surprising, but the need for these better initial conditions has not really been stated, especially from a satellite side, within NESDIS. We have some initiatives that are going into the Arctic action plan to try and improve this. So somewhere it is being vetted, but we don't even have things at even a lower level. They're being asked for to really supply the types of things, satellite-based products that we know are forthcoming, but we don't have a requirement in from NCEP to help drive them. So it would be very helpful to have that kind of a requirement in place, and be working more in lockstep with NESDA or with NCEP and meeting your satellite-based requirements.
Yes, If any additional, because CS thickness is such a difficult field, so any additional information would be great, very helpful.
Okay, I know that there is a CICE thickness product on the way from JPSS and GOES-R projects. They're probably not looking to be able to meet the multi-year requirement that you are demonstrating within your product. So they're only going to be good for the first meter and a half. And then after that, it's pretty much a bit of guesswork. But in order to be able to make sure we're getting in some of these other products, like the biomass, where we could actually try to get these things operationalized, or even ISAT-2 will not help, because the requirements never came in to NASA to have it where this would be something that would be produced in near real time. It's almost going to be a month and a half after the product is generated before you'd see the results.
Yes.
Or after the overpass before you'd see the results. So making sure we have some solid requirements can help us vet and make sure these products are coming out in near real time towards your direction.
Yes, definitely.
Okay, thanks for the comments, Sean. Next question is from Stan Benjamin. Stan, are you on the line?
I am. Thanks a lot, Dan. Thanks for a good talk. Shan's son and I are sitting here just curious a little bit more. Can you tell us briefly about the physics changes to get this much better annual cycle for the ice in CFS version 2?
You asked about the physics part?
Yeah, what physics changes, because obviously that was pretty critical in getting the cloudiness correct. Can you say briefly what's being done in that changed version to get that better annual cycle over the Arctic?
Yeah, for physics part, there's one thing that is kind of intentional. That is the lower clouds are turned off in the standard model setup because of another reason, not because of this highlighted assimilation. So there are too few cloudiness in the current operational model, and if we are looking at the same slide, see this is the problem we're talking about. The model was not able to produce the CS here, which is because our explanation is because of the warm SFT anomaly and warm baths, which in turn is because of too much solar radiation, and which in turn is because of too few cloudiness. So for this particular thing, in our study, we just turn on the cloudiness back. So this
the shallow cumulus?
Yeah, stratus clouds basically. It's stratus cloud. Yeah, but this may degrade other things like ISO or in the tropics, but surely it helps improve CS prediction.
Okay, thank you.
Okay, thanks for the question, Stan. And then final question for Wanchu is from Florence Federer. Florence, are you on the line?
Can you hear me?
Yeah, we can hear you, Florence.
Oh, great, thanks. Yeah, so the question I'm home with a cold, so I hope you can hear all right. The talk before yours was on shorter term forecasting, and your focus is seasonal or longer.
Yes.
So you talked about the need for a better CICE thickness for initialization. Can you talk about the difference as it relates to those two time scales? You know, obviously it's important to have good see, every initialization field is important, but I think perhaps it's more important for the seasonal type forecasting that you're more interested in. Would you just make some comments on that, the time scale?
Yeah, you're right. I'm talking about the seasonal time scale. For shorter time scale, like weather, a few days or a couple of weeks, I think the initial CS concentration will be very important, the accurate initial concentration. And also the atmospheric initial state is also very important. And the model skill to predict the weather timescale, synoptic timescale variations. So that is probably more important than CS thickness. Thickness is more important for longer timescale. That's my understanding.
Yeah, there's probably some intersection with Sean's comments about the ice edge from passive microwave versus ice edge from a more operational analysis. I agree with him, but I think there again the time scale that you're talking about and that you're using that ice edge or that ice concentration as validation for your model development. Again, you have to take the time scale forecast into account when you're thinking about what product to use for validation.
Yes. Yeah. We are trying. Yeah, we will try to use other products too for the verification, and even for experiment to test how important is initial SH or impact on the forecast at different time scales. Thanks.
Okay, thanks for the questions and comments, Florence. And WAVEWATCHIII, thanks for fielding so many questions and comments. Appreciate that, and thanks for the talk. So before we sign off, there was one question that came in through the chat for Hal Ritchie. And Hal, I'm wondering if you're still there?
Yes, I'm here.
Okay, great. So I'll paraphrase this. This person was interested in whether the systems are operational and live, whether the data for the system is available online, both in terms of the current values and also retrospective values, and over what time scale. And this person's interested in CICE cover, but perhaps other products as well.
Okay. The different components, I would say, are in different stages of being operational. We are actually setting up an access through a web-based system. It's not fully in place yet, but we do intend to go that route. So if there's a specific individual that would like to send me an email request, I could forward it to the folks that are setting that access up. But at the moment, it's not fully operational. Although I expect some products are probably available through the Canadian Ice Service. So I could relay an inquiry or a request if one were sent to me.
That's great. Thanks a lot, Hal. So the question was from Matt Horn. And Matt, if you're still on the line and you can't find Hal's email, feel free to send me an email and I can connect the two of you. Happy to do that. So that's it. So thanks, everyone, for attending this webinar, and thanks to our three presenters. Really great series of talks on these activities in the Arctic. Really appreciate your time presenting in this webinar. We have a webinar next month, February 10th, and it's going to be on the topic of weather and climate linkages and focus on a variety of different elements of the weather to climate interface, including analysis of certain extreme events and other events, modeling efforts at this time scale, and prediction efforts. And our three speakers are going to be Chris Bretherton, who's at the University of Washington, Marty Hurling, who's at NOAA Israel, and Matt Johnson, who is now at NOAA GFDL. So I hope that everyone's able to join again next month. And again, thanks, everyone, for joining this month.
Thank you.
Okay, thank you.
Bye.
Take care.
Bye-bye.